Hello everyone, this is sixth video on sequence and infinite series. In the previous video, I have explained you about the infinite series and how to find out the convergence of the infinite series using the sequence of nth partial sums. And today in this video, I am going to explain what is the geometric series and what is the geometric series test. So how will you check the behavior of the geometric series? So I am going to explain these two. So now first of all, see what do you mean by geometric series? Any series of the form a plus ar plus ar square and so on, ar to the power n minus 1 and so on, where this a is the first term and r, this is said to be the common ratio, and both these are constants. Moreover, a is a non-zero constant, right? So any series of this form is said to be the geometric series, right? For example, if you see a series of the form 1 over 2 to the power n, where n is varying from 1 to infinity, this is geometric series with the first term as half and the common ratio as half. So once again, see what do you mean by geometric series? So any series of this form is said to be geometric where this a is the first term, r is the common ratio, both these are constants, and a should be non-zero. Okay, so now the next motive is to check the behavior of this series, and that is said to be geometric series test. Now just see what is the geometric series test. Now this test says that let you are having a series of the form, let this be the geometric series with first term a and common ratio r, then the series a r to the power n minus 1, this is convergent if the mod of r is strictly less than 1 and divergent for r greater than equals to 1, for mod of r greater than equals to 1. So this is the geometric series test, which says that let's suppose you are having any geometric series with the first term a and the common ratio r, then this series is convergent if the common ratio is lying between minus 1 and plus 1, otherwise it is divergent. So now just see the proof of this. For the proof, we will use the sequence of partial sums. So we'll find out Sn. What is Sn? It denotes the sum of first n terms. So add first n terms. Right? So this is the sum of first n terms. Now you multiply both sides with r. Now you take the difference of these two. Now just see, these terms are cancelled out. This term will be cancelled out with the term which is over here, right? So you left with this term and this term, right? Now you can take a to be common. you will have this. So now if your r is not equal to 1, then we can divide by this 1 minus r. So we can take 1 minus r to be this side. So you will have this thing, right? So this is your sum of first n terms, where this a is the first term and this r is the common ratio. So next we will find out the limit of this Sn. If this limit is finite, we will say our series is convergent, otherwise not. So find out the limit as n approaching to infinity, Sn. Now this will be the limit n approaching to infinity, a 1 minus r to the power n upon 1 minus r. This will be what? Now just see, whenever your mod of r is less than 1, then the limit n approaching to infinity of Rn will be 0. So your sum will be a upon 1 minus r, which is a finite number, right? But if your mod of r is greater than 1, then this is approaching to infinity. Just like if you have r to be, let's suppose, half, then 1 by 2 to the power n, this will be goes to 0 as n goes to infinity. But if your r is greater than 1, let's suppose 2 to the power n will goes to infinity as n goes to infinity, right? So therefore whenever the mod of r is less than 1, this term is going to 0 as n goes to infinity. So you left with the sum of the series as a upon 1 minus r. However, whenever mod of r is strictly greater than 1, this term is going to infinity, so you will have this sum as infinity. So what this implies? This implies that the given series a r to the power n minus 1 is convergent for mod of r less than 1, right? And divergent for mod of r greater than 1. This is less than 1, sorry. So whenever mod of r is less than 1, this is convergent and divergent for this. Now the case left when r is 1. Now when r is 1, what will be your sum of first n terms? Put r to be 1, a plus ar, r is 1, plus ar square, r is 1, and so on up to a. So you will add a n times. So what is the sum of first n terms in this case? It is n into a. And when you find out the limit as n approaching to infinity of Sn, what will you have? You have this is infinity, because our a is any non-zero finite number, right? So this is approaching to infinity. So again, the given series a, this is divergent when your mod of r, or you can say when your r is exactly 1. The same when your r is minus 1, then what will happen? Again your Sn is a minus a, then plus a, then minus a, then plus a, and then minus a, and so on, minus 1 to the power n minus 1 into a. Now again, when you take n tending to infinity, Sn, it is not a finite value. Either it approaches to 0 or it approaches to a, provided your n is even or your n is odd. Now just see, when your n is odd, let's suppose 1, so 1 minus 1, it is 0, you left with only first term which is a. When your n is even, so you will have a minus a minus a, so these terms will be cancelled out and you left, the sum is approaching to 0. So your limit is not unique, right? So that means your series is not convergent when mod of r is exactly 1. Either it is 1 or it is minus 1. In each case your series is not convergent, right? So this completes the proof of geometric series test, the given series is convergent whenever your mod of r is less than 1, and it is divergent whenever your mod of r is greater than equals to 1. So we can use this GP series test to check the behavior of GP series. For example, let's suppose you are given a series of the form minus 1 to the power n into 5 divided by 4 to the power n, where n is varying from 1 to infinity. Now just see what will be your series. It will be minus 5 by 4, then plus 5 by 4 square, then minus 5 by 4 cube, and so on. Here your first term is minus 5 by 4 and the common ratio is minus 1 by 4. So by GP series test, since the common ratio, which is 1 by 4, is strictly less than 1, so therefore the given series is convergent, right? So in this way we apply the GP series test to check the behavior of the series of this form, right? Now just see one more example. Let's suppose you have to check the behavior of this series. So now this is 5 plus 5 into 3 by 2 plus 5 into 3 by 2 whole square, and so on. So this is GP series with the first term as 5 and the common ratio as 3 by 2. Again by GP series test, since the common ratio, this is strictly greater than 1 in this case, which is 3 by 2, so therefore the given series is not convergent.